I will record this discussion and the discussion on Thursday, and then post those to Canvas. So, yeah. And I can also, if people are asking questions in office hours, I will continue the recording into office hours. But okay. Does anyone have any questions about these review sessions or about office hours or just logistical questions about the midterm? Okay. Hearing nothing. So the topics that I potentially, so in the absence of other questions, the topics that I wanted to run through for review today are conservative vector fields. So, what they are, how you can determine if something's conservative, what kind of properties they give you. And then surface integrals. So surface integrals is something that we have not seen on our quizzes yet, but it is probably going to be a big topic on the second midterm. So again, wanted to go through like how you compute them and then some examples of those. And then I guess technically it's a surface integral. So also flux through a surface. So based on the practice midterm, it seems like these are the most important topics and the ones that are, well, the most important ones that are also like more complicated than others. So I wanted to run through those. And then one other thing, I'm going to open up breakout rooms that you guys are welcome to join or not join if you want to. So if you want to break off with other people and talk to them about any topic or the practice midterm, feel free to join one of these rooms. I will be in here, so I won't be coming around, but if you want the chance to talk to classmates, those are open. So yeah. Okay, let me make sure there was another topic I had. Okay, does anyone have any specific questions that they want me to go over first? Otherwise, I will just get into these two review topics. Yes, no quiz today, just review.
Is it possible if you can sort of go over just finding parameterizations for 3D surfaces?
Finding parameterizations for 3D surfaces?
Yeah.
Yeah, we can do that. So yeah, we can do that. I'll just add that in. Because that, oops, I didn't mean to change color of that. Because that is something that wasn't specifically on the practice midterm, so I will happily go through it, and I'll go through it first. I'm not going to spend super long on it, but I will go through it. And I guess it also extends to other, surfaces and regions, so it will be helpful. Okay, so let's do that first then. Okay, so parameterizations. Of regions. Do you want me to go through some examples of this? So do you want me to go like roughly through what my, like when I am looking at a surface, what my thought process is for how to parameterize it?
Yeah, the second one works.
Yeah, okay, cool. So when you're looking at a 3D, region, you kind of have to run through the various tools that you have to parameterize it. So the first thing I always think about is I think about what coordinate system is the best to parameterize this. So which coordinate system? And often Often this will be pretty obvious. So we have normal Cartesian, which is just x, y, and z. We have cylindrical, which is r, theta, and z. And then we have spherical, which is r, theta, and phi. I don't remember if Professor Wong normally writes this in that order, and she also uses that, or the other order. But yeah, so Cartesian, we've all worked with this forever. This is just straight up specifying like it is this far in the y-axis, this far in the x-axis, this far in the z-axis. So Cartesian coordinates work really well for systems that are roughly box shaped up to some like squiggliness, which is a very rough way of saying that. But like if you have a kind of rough structure where you have like a surface up here that does kind of whatever, and it goes down normally and does whatever, it's a great time for Cartesian coordinates. If there's kind of like clearly defined like sides of something, so if you know you have something that does whatever over here, something over here, and there's stuff in between, these are kind of things that normally work in Cartesian. And then also a really great way to, actually I'll just do that. I'll explain that idea in the end. And then cylindrical coordinates, you know, you're describing points based on how far they are from the z-axis, what their angle is from the x-axis, and then how far up they are from the xy plane. And so cylindrical coordinates work super well for surfaces that, you know, are being rotated around some axis, or they have some sort of nicely varying like rotational property, and then are just straightforward in z. So you might have a certain, so I mean, obviously the straightforward example is just a cylinder like that, but you can also make it a lot wigglier. So if you have kind of this shape that has some way of parameterizing, so r can be written as a function of theta, and then it just extends downwards normally in z. So kind of roughly those shapes work for cylindrical. And then spherical is perhaps the most complicated of them. Spherical works great when things only depend on angles and only depend on how far you are from the origin. So spherical coordinates, you describe it by the distance from the origin, the angle down from the z-axis, and then the angle in the xy plane. And if I switched phi and theta, someone please speak up and stop me. But so this is your point, r theta phi. And then spherical coordinates work for, you know, things that really only depend on your radius. And then, so unfortunately, there's no set way of actually determining which one of these go to which, or which region you should parameterize with these. But the best way I've always found of doing it is just simply what equations describe your region and what variables are those in. So if your equations are really strictly in x, y, and z, you should use those. If your equations have an x squared plus y squared, cylindrical is probably your way to go. And if they have a x squared plus y squared plus z squared, then it's spherical. Okay. And then, so once you've picked your coordinate system, kind of the only thing left to do is you need to look at your region and vary one of those variables and see what it goes between. So I think the easiest example of this, of course, is just with something in 2 dimensions, and then it kind of generalizes to 1 dimension. So if you have this region that's bounded below by f1 of x, above by f2 of x, on the left by g1 of y, on the right by g2 of y. So because we have these x and y's, we're going to describe in the Cartesian coordinates. And then, so what's going to happen is you're going to look at one coordinate, see what it varies between, then look at the other coordinate. So if you're looking at this, I guess actually this is perhaps overly confusing. So I'll make it a little bit simpler and just vary it from A to B. So if you're looking at, so we have x and y as our coordinates, you look at x first. So if you pick some arbitrary y and you let x vary, then the region you're integrating from goes from this left point, which is A, the right point of B. And so you have A less than or equal to x less than or equal to B. And then you want to fix some x point and let y vary. So if you want to look at, say, this line, and the region you care about runs here from this bottom line, which is f1 of x. And then it varies to up here, which is f2 of x. So I've always found it really, really helpful to draw a figure and then literally draw lines through it and see what those lines hit and which one it hits at various points. And then the same idea can be applied to other surfaces. So if you're looking at, say you're again looking in the XY plane, but now you're considering this circle here. So because we have this kind of nice rotation, we're going to describe this in cylindrical coordinates, r theta. And then, so looking at how r varies, you start r at the origin, it starts there, it goes outwards, and it hits that outer region, at which you can describe this outer region by cosine of theta. Yeah, that works. And so if you look at r varying, r starts at 0 and runs outwards to cosine theta. And then if you start looking at, so then to look at theta is a little bit more complicated. You kind of have to look at these like half circles. And if you kind of look smaller and smaller, these half circles need to vary all the way between 0, or not 0, negative pi and pi. So was this description actually helpful, or do you want me to do a more explicit example?
That's perfect. Thank you. It helped a lot.
Cool. Glad to hear it. Being able to parameterize these surfaces and these volumes is kind of the trickiest thing in this entire class. So yeah, it's definitely a good thing to practice, and it will definitely come up on basically everything you see. Okay, so I want to go over conservative vector fields really quick. So conservative vector fields. So I want to review them and then go through an example or two with how they work. So conservative vector fields, definition of them, that's not how you spell definition. That's the reason. So the definition of a conservative vector field is some vector field that can be expressed as the gradient of a function. And so we have this vector field f that takes in points in Rn, spits out vectors in Rn, and then we have a function f that takes in points in Rn and spits out real numbers. Okay. So this is the strict definition. You can always come back to this one, regardless of what space you're working in. If you can show that this function f either exists or doesn't exist, then you'll see if it's conservative or not conservative. And then conservative vector fields, we care about them because they have some really nice properties. So the first really important, or I guess actually the only property that we really care about is path independence. So if we have some conservative vector field f, it can be written as the gradient of this lowercase f, then regardless of what path we integrated over, this integral only depends on the endpoints. So C here is a path that starts at A and goes over to B. So regardless of how our path goes from A to B, the only thing that matters is that we start at A, start at B. You can always evaluate this integral by taking the difference of your potential function, which this is called a potential function. And then this also leads to the nice property that for any closed loops, a conservative vector field is going to integrate to 0. So if we have some curve C that starts at A and returns back to A, then the integral of f over this C is always going to be 0. And then these two properties, you can actually show pretty easily that they are equivalent, and you can use one to show the other or vice versa. So when it comes to actually showing that something is a conservative vector field, you can always go back to the definition, but the definition is really nice if you want to show that something actually is conservative, but it gets pretty difficult to show that something's not conservative with the definition, because that kind of runs into like, how do you show this thing doesn't exist, which is a whole difficulty. So there's some other ways that you can determine if something's conservative or not. So first off, so if a vector field is conservative, then the curl of it is 0. All right, so this again works on any region. If you know it's conservative, then the curl will be 0. If you have some vector field and you can show that the curl is non-zero, then that will automatically imply that it is not a conservative vector field. So you can also do this in the backwards direction. So if the curl of f is not 0, then f is conservative. Then we also have the reverse direction, though in the reverse direction, we need to be careful about what region we're talking about. So in a simply connected domain, the curl of f being 0 implies conservative. And then as a brief reminder, so simply connected, intuitively, I think you meant not conservative. Yes, I did. Thank you. Not conservative. Thank you for that, Brian. Okay. But in a simply connected domain, the curl of f being 0 implies that it's conservative. And simply connected is just a fancy way of saying it doesn't have any holes that go all the way through. So regions that have a hole in the center aren't simply connected, but regions that say have a hole that extends all the way to the boundary are simply connected. And the way of actually testing if something's simply connected or not is if any closed loop can be squeezed down to a point. So in some region like this, if you draw a closed loop in here, you can squeeze this down into a point. But if you have some region that has a hole in the center, and if you draw a loop around that hole, you can't squeeze it down to a point because it always gets caught on that hole. So there's that. Okay. So I have a couple examples that I can go through of conservative vector fields or examples of showing whether or not something is conservative. Do people want me to run through that? Or do people want me to go on to surface intervals? Okay, you would like to see examples. Perfect. Okay, so to encourage like not necessarily participation, but to encourage some practice on your guys' part, I'll give an example, give you like 2 or 3 minutes to think about it, and then we'll come back together and talk about it. So the first example is the vector field f is equal to z over x, z over y, ln of xy in the region x, y, z, such that x is non-zero and y is non-zero. So the question is, well, is f conservative? And yeah, I'll give you a minute or two to work on it yourself, and then we'll talk about it as a group. Okay, so is anyone feeling confident enough that they'd like to share um, what their answer is and how they arrived at it? Okay, that is totally fine. So looking at this vector field, we have two different options for showing whether something's conservative. We only have two options. So we can either do the curl method, or we can find a potential function, or find that, yeah. So yeah, Jordan, what you said in chat is correct. So we will be finding just straight up a potential function for this. So in this case, so this region that we have here, so excluding x equals 0 for x non-zero and y non-zero. So this can be thought of as the plane. So we're looking at 3D space, but we're not considering, so I guess I should probably, so we're in 3D space, but we've removed the x-axis and the y-axis. And so this is a space that is not simply connected, because we can draw a loop around any one of these axes, and this loop can't be shrank down to a point. And so actually, Okay, so in this case, we can't do the curl method, so we have to find an explicit potential function. And the potential function that Jordan recommended in chat exactly works. So we can use the potential function f x, y, z is equal to z ln of xy. And then some pretty straightforward computation shows that, did I write this one wrong? Yeah, no, so some pretty straightforward computation shows that this has the properties that we want. Partial y equals z over y, and partial f of partial z is equal to ln of xy. And then the actual way of going about and constructing these potential functions is essentially you just take each component of this vector field, you integrate it, or you find an antiderivative of it, and you see if you can mesh them together in some nice way. So, so we can't do, yes, we cannot do the curl method because the space is not simply connected. This is correct. Yeah. Okay, so we're going to look at each of the components. We're going to take an antiderivative and we're going to see if we can piece them together. The easiest component to start with is the z component. So the x component and the y component both contain x and y. So finding the antiderivatives of those is going to be a little bit complicated. But if we look at the z component first, so we have that partial f partial z is ln. So I guess this is the answer. This is how to get to the answer. But so partial f partial z is ln of xy. And so we know that f is going to be z times ln of xy plus some function, not f again, plus something that only depends on xy. And then luckily for us in this case, so we're luckily for us in this case, if we consider just this term, we can differentiate each of this by x and this by y, and we actually get our final answer. And then if you didn't notice that this z term is really easy, what you can also do is if you look at, so we have partial f partial x is z over x. And so we know that f has to be z times ln of x plus something that only depends on y and z. And then we also know that partial f partial y, so that is z over y, which implies that f is z ln of y plus some function that only depends on x and z. And then these two, you can just combine them by adding them together. And then that also works well with our z component. So I guess the general strategy is if you can't do the curl method, you look at each term individually, you take antiderivatives of them, and you see if there's some way you can piece them together by adding, or just if it just happens to work out. Yes. Okay. Does anyone have any questions on this vector field specifically? Okay. Hearing none, I want to I think it'd actually be more useful to go into surface integrals. So this is kind of like a situation where the region that you care about is not simply connected, is the most complicated that it can get, really. So I think this is a good example. And then if people want, I will go over more examples after discussion during my office hours. So I will be moving on to surface integrals. So surface integrals is something that we haven't seen in a quiz before. But thankfully, it kind of falls out in the exact same way that line integrals do, just with one extra dimension. So we have some surface that looks like whatever. So we have this surface S, and we have a vector field F. So this is a vector field, or no, we're not starting with the vector field. We're just starting with a normal real function. So we have some function F that takes in points in R3 and spits out real numbers. And so we want to integrate this function F over the surface. We're going to integrate F ds over the surface S. This notation using S there both times is confusing and I don't like it. But it is pretty standard notation. So we're going to continue that. And so just like line integrals and just like vector volume integrals or whatever, what we're going to do is we're going to parameterize the surface, and then we can break it down and eventually extract like a nice two-dimensional integral over some region R. And so what we're going to do is we're going to parameterize the surface U as a function G that takes in so the surface S as a function G that takes in parameters UV and then spits out our surface. So we find this function G that takes in UV, where U and V are points in some domain D. And I'll give an example of actually finding this domain in a second. But if we can parameterize the surface in this way, then we can compute the normal vector to this parameterization G. So the normal vector at some point UV will be given by the partial derivative of G with respect to U crossed the partial derivative of G with respect to V. And then we can compute this integral of F. I don't know why I scrolled down. So we can, with this parameterization, we can compute the integral of F as the integral, or the two-dimensional integral. My eraser is not working. Okay. So we can compute the integral of F as the integral over D, F with G on the inside, times the norm of the tangent vector, which is also a function of UV, dA. So just like how we took line integrals, parameterized them, multiplied by the magnitude of something, and then we got out a standard like one-dimensional real integral, we can do the same thing here. We parameterize the surface, we compute this normal vector, take the magnitude of it, and then we've rewritten our surface integral as an integral over some region that is just in normal two-dimensional space. Okay. And then, so an example of this, I guess, does anyone have any questions on like the abstract formulation of this? Okay. Hearing none, I'm going to go over this example. So an example of this, so let's consider we have a surface. So we have the surface that's described by z equals x cubed with x varying from 0 to 1, y varying from 0 to 1. Yeah, with x varying from 0 to 1, y varying from 0 to 1. And we just have some arbitrary integral, or arbitrary function f that takes in points in R3 and spits out real numbers. So, this surface, so this surface It's varying from y 0 to 1, x 0 to 1, and then z is going to look like x cubed. So it's going to look kind of like this. That was a horrible second. And then this is the surface flowing down this way. Okay, so to parameterize this, we basically are given all the tools that we need currently. So we need to pick, like, we need to find our function g. Function g is going to take in points in some region in two-dimensional space that we'll call D, and then it's going to output this surface. So with this one specifically, our best idea is going to be, we can take this region below our curve. So this is a region in R2. We can call this our region D, and we can define G on this region as G of UV. I guess actually, to make it less confusing, I'm just going to reuse X and Y here, if this would ever erase things. So G of XY is going to be equal to, so the Y component or the X component doesn't depend on anything. So it's just going to be X, or so this surface, the X dependent does the X component doesn't change anything from the normal rectangle. So it's just going to be X. Same thing with Y. And then our Z is going to be X cubed. And then our region D, I guess I should specify that our region D is just going to be 0, 1 cross 0, 1. And then to actually compute this integral, we need to compute the normal vector. So our normal vector, we need to find these partial derivatives. So partial G, partial X is going to be 1, 0, 3x squared. And then partial G, partial Y is going to be 0, 1, 0. And this gives us that our normal vector as a function of X and Y is going to be these two vectors crossed one another, which we can do in the normal way. So our X component is going to be, okay, so our X component, we can do that standard like crisscross thing. So our X component is going to be these, or so 0 times 0 minus 1 times 3x squared. So we'll have negative 3x squared. Our Y component is going to be not that way. These two, the difference of these two, which they're both 0. So we're going to have 0 there. And then our Z component is these two multiplied together minus those two multiplied together. And so our Z component is just going to be 1. And that gives us the magnitude of our normal vector as a function of xy is going to be the square root of 1. I'm doing that in a weird order. Okay. So that is going to be 9 x to the 4th plus 0 plus 1. And then if we want to compute any integral, the integral of any function f over this surface S, we can then rewrite it as stupid eraser. So we can rewrite it as the integral from 0 to 1, integral from 0 to 1, f of g of xy times the square root of 9x to the 4th plus 1 dx dy. And then from here, it's just a straightforward 2D integral. Okay. Does anyone have any questions on finding the parameterization of that space, or finding, once you have the parameterization, actually setting up the interval. I know I went through that quickly. But. Okay. In that case, I do have another example that I think is useful to run through. So another example of this. So we have the plane. So our surface S is going to be the plane x plus y plus z equals 1, restricted to the region where x squared plus y squared is less than or equal to 1. So let f g x y be x cubed. So in this specific case, I haven't actually specified what f is. So f g x y is going to depend entirely on what f is. So if, for example, I'll move this down. My tablet is really not happy with it. So if, for example, we have the function f of x, y, z is equal to, say, is equal to x, then our function f of g, x, y, is also just going to be x. But if we instead have a function, say, f of x, y, z is equal to z, then f of g, f composed of g of x, y is going to be equal to x cubed, because we take the z component and stick it into the z there. Okay. Yeah, so it's entirely dependent on what your function actually is. But yeah, and I will admit that using x, y here, while it does make like this parameterization easier to see, it does lead to some confusion down at the end here, because we already have x, y, and z, and then we're plugging in x and y. So that's why people normally use u and v here as our new variables. But obviously I did not. So, okay, as another brief example, we have the plane x plus y plus z equals 1, restricted to the region where x squared plus y squared is less than or equal to 1. So this plane looks kind of roughly something like, I actually don't know how to draw this. We have this plane that kind of looks something like this. It extends downwards and outwards. Planes are difficult to draw in 3 dimensions. And then we're restricting it to this kind of cylinder going upwards. This is an awful drawing. I guess, so when you actually do the restriction, what you find is that what this looks like is this kind of tilted disc here that goes through the origin and is tilted upwards in each positive direction. So if you kind of looked at it sideways, it'd be tilted this way. If you looked at it along any coordinate direction, you're going to get this tilt. And we want to parameterize this. So we can kind of, in the same kind of way that we did last time, a nice way to find this region D would be to like project the surface down onto the XY plane and then just determine it in terms of Z. So we're going to consider the region D that is just the inside of the circle, x squared plus y squared is less than or equal to 1. And this is in the space R2. And then to actually, so we're going to have our function g from D to R3. And now we need to actually compute this. So because we're projecting it down onto this XY plane, our X and Y variables aren't going to change. They're just going to be U and V. And our Z variable is the only one we really care about. And then, so we can take this equation here and rewrite it as Z is equal to 1 minus X minus Y. So then when we write this in terms of our U and V, our parameterization is going to be U, V, 1 minus U minus V. And then from there, we do the standard things. We compute partial G, partial U as 1, 0, -1, partial G, partial V, 0, 1, -1. And then we can compute the normal vector, which will be so 0 minus -1, 1, 0 minus -1, 1, and then 1 minus 0. Does it really work out like that? This one, huh. If I did that correctly, feel free to speak up, but I think that works. And then from there to actually compute it. So this one's nice because your normal vector has a constant magnitude of √3. And so actually calculating things is pretty straightforward. All right. So I will happily answer any questions about this example, but I do want to let people know that it is after 4:50. So you have absolutely no obligation. Well, you never have any obligation to stay. You especially don't have any obligation now that discussion is officially over. So if you're going to leave, best of luck in the midterm. You guys all did very well on the first one. So are the bounds for U and V -1 to 1? Sorry, I'll finish my thought. You guys all did very well in the first one. So I feel like you're probably going to do very well in the second one, but best of luck regardless. Yeah. Okay, so when will we be hearing back about the trial? Okay. All right, I will address these in order. So are the bounds for U and V -1 to 1? No. So if you look at, it's not shown well in this picture, but what we did to get this parameterization is we took this kind of tilted disk we had, we projected it down to the XY plane, and then what we got is the circle, or we got the circle plus its inside. And so U and V, so U and V are varying inside this region, D. I don't know why I didn't circle the D part. And so you can vary like U from -1 to 1, and then V is going to vary from negative √1 minus U squared to positive √1 minus U squared. So you have to do the same kind of parameterizations, the same kind of expressions that you did back in the two-dimensional or the 2D integrals. When will we be hearing back about the challenge problem set? So the challenge problems are being graded this week. So the person who was responsible for grading them had just a very busy week, so he didn't have a chance to get to it. So he's getting to it this week, and he is planning on having it back before, or his like deadline is to have it back before next week, because next week is the next challenge problem set. So next week's challenge problem, so we'll have discussion again to work on them. The challenge problem is going to be on non-orientable surfaces, which is surfaces that you can't like take a consistent normal direction because somehow it reaches a contradiction, which is actually a really cool topic, so it should be fun. But that is next week. And you will hear back about the first problem set before next week. And then you do have a chance to submit revisions for that. So what would the bounds be for this problem? Yeah, so U and V are inside this region D, which is the circle. So U and V, so we have this relationship that U squared plus V squared is less than or equal to 1. And this kind of defines D. So what we can do is we can parameterize. So I guess here I'll draw that out. So our region in terms of U and V is the inside of this circle of radius 1. And so what we can do is, can you always, okay, hold on. So this very nicely is a V simple region. And so we can just let U vary from -1 to 1. So U goes all the way across here. And then our V is going to vary between -√1 minus U squared to square root of 1 minus U squared. And then this is just the like this is the same method that we use for X and Y stuff. Okay. Can you always parameterize the surface by G UV equals UV Z UV? That's actually a good question. No, you cannot always parameterize it that way. And the reason is that it's possible that Z isn't actually expressible as a function of U and V. So an example of this would be like, if we considered a surface that was, say it looked something like this. You don't need that line there. That looks worse. And it's not erasing the other one. Okay. So if we have some surface that looks like this, for example, the idea of like parameterizing this strictly in terms of X and Y would be to like project this down into the XY plane. And then you'd get some rectangle here. And then you'd have to write Z as a function of U and V. Hey, Jane, I'm just answering a quick question and then we'll get started on your makeup quiz.
Cool, thanks.
Okay, so the idea would be to like project this down onto the plane, let U and V vary. But the issue is that you can't express Z as this function because there are 2 points that are associated with any given U and V. And so for this case specifically, what you want to do is you could project it over here to the XZ plane and then parameterize it like that.
I guess my question regarding this is like, we were talking about how you can parameterize using like cylindrical coordinates and spherical coordinates. And I was kind of wondering if we could always just use this method where you just project the surface onto one of the planes and just write it like that.
Yeah, unfortunately not, because of these kind of overlaps. So I guess the example where you couldn't do it anywhere would be like a sphere. So if you had this stupid or this, so yeah, if you had the sphere, then your issue would be that if you project it onto any 3 of those, or any plane, then you're always going to have this. There's always like 2 points associated with any one point in the projection.
Okay, that makes sense. Thank you.
No problem.